Ladies and gentlemen, good evening. Welcome to the Geological Society of London and this lecture titled Lakes Beneath the Ice. My name is David Shilston. I'm the president of the Society. This is the 10th and final lecture for 2013. It's also the last lecture that Shell UK will be sponsoring, which is a pity. Shell has sponsored the London lecture series since it began in 2007 as part of our Society's bicentenary celebrations. It's my pleasure to thank them on behalf of the Society and for all their generous support over the last 7 years. Over that time, the lectures have developed a strong following and have become an important part of the Society's public outreach. So I'm pleased to report that the lectures will continue into 2014, but under the banner of the Geological Society, London Lectures. And on the back of the flyer, you'll see the list that we're developing for next year. Now, turning to this evening's lecture. Attempts to measure and sample subglacial Lake Ellsworth directly were unsuccessful in the recent Antarctic field season last November and December. Why did the experiment fail, and what did we learn from that failure? To explore these challenges today, we welcome Martin Siegert, Professor of Geosciences at Bristol University and Principal Investigator of the NERC Lake Ellsworth Consortium. Martin, who was previously Head of Geosciences and Assistant Principal at Edinburgh University, has been a UK delegate to the Scientific Committee on Antarctic Research. It was his use of penetrating radio echo sounding to uncover the landscape beneath the ice that enabled him to discover and map Lake Ellsworth for the first time. Ladies and gentlemen, please welcome Professor Martin Siegert.
Thank you ever so much. I was asked to do this talk more than 12 months ago, and I thought when I accepted that what I would be telling you today would be all the lovely secrets in science from subglacial Lake Ellsworth, but I suspect you know, in fact I know you know because that's what's just been announced, that that's not the case. It's not the type of lecture that I'm giving you. So it's a sort of Christmas story. Finishes at Christmas, you'll see, but it doesn't yet have a happy ending, not yet, but we remain positive. The type of talk I'm going to give you is very much along the lines of how we learn lessons from failures in science. And in many areas of science, we have to understand that that's what it's like. And the research isn't just all about the final results. There's a sort of learning process you have to do. And in particular, when we're trying to conduct science at the frontier, at the edge of what we know. Anyway, let me go on and you'll find out what I'm talking about. So subglacial lakes in Antarctica really became interesting from a scientific perspective about 20 years ago. I was really fortunate to be involved in this paper that got a lot of coverage. It was in Nature, got a lot of coverage around the world. When we discovered the size and shape of Lake Vostok in East Antarctica. Lake Vostok is about the 5th largest freshwater lake in the world. It's 200 kilometers long, 50 kilometers wide, and it's about 500 meters deep. Actually, you know it's a little bit deeper than that in some places. And it sits beneath 3 or 4 kilometers of ice in the middle of East Antarctica. We discovered subglacial lakes 20 years previously to this, but they never really acquired academic interest and traction around the broader community. And it took this paper for that to change. And the thing that changed was that microbiologists suddenly became interested in Lake Vostok, and indeed other subglacial lakes, as being viable habitats for life. And geologists were interested in this lake in terms of what the sediments on the floor of the lake, and there will be sediments on the floor of the lake, what they can tell us about glacial history and ice sheet history. The idea being that the sediments on the lake floor will be much older, contain a much older record of change than the ice core in the ice above, although that's a wonderful record going back 400 or so thousand years. So that was the motivation. We know subglacial lakes are there because we undertake airborne ice-penetrating radar reconnaissance surveys of Antarctica. In the 1970s, the platform of choice was a Hercules C-130 aircraft, the cartoon of a Hercules, and the cartoon shows radio waves of high frequency, 60 megahertz, being thrown into the ice sheet, and you get reflections where there's a change in the dialectical properties of boundary. So there's a reflection at the ice surface between the air and the ice, there's lots of reflections within the ice. It's essentially, it's like strata within the ice sheet. And then you get reflections from the bed of the ice sheet. And the type of reflections you get from an ice-water interface on the top of a lake is distinct from what you get from ice sediment and ice rock interfaces. To give you an example, there's this one. This is my favourite subglacial lake from airborne radio echo sounding. So the third of the line there, that's the ice sheet surface. You can see all the strata within it. And the hyperbole you get here, just like seismic sounding, that's from the ice bedrock. And that really flat, bright thing there is an ice-water interface from a subglacial lake. It doesn't really need to be a genius to work out the sidewall slopes here indicate that this lake, that's about 3 or so kilometres, a bit more than that deep. So that's about a kilometre of topography over there. You've got some pretty serious side slopes going into that. This is going to be several hundred, tens, maybe a few hundred metres deep, this particular lake. Okay, so that's what we know they're there. But why are they interesting? Well, that paper that was in Nature really pushed out the idea that subglacial lakes are interesting from a life in extreme environments perspective, but not just can they hold life and can they contain life, what type of life is it, how is it living, is it flourishing, is it on the edge of existence, what processes is it using to power the life processes, how does it actually work, and of course in the sediments on the lake floor, what do they tell us about the ice sheet history in West or East Antarctica, depending on which lake. So those are the two scientific drivers. In fact, we can hypothesize about these things, that subglacial lakes do contain life, and they do contain records of climate change on the sediments, and those hypotheses are testable. But you have to acquire samples in order to test them, and that's really what we're trying to do with the Lake Ellsworth project. So the work that we're trying to do has never been done before, so there's no blueprint to follow. It's right at the frontier of science, discovery. It needs a level of engineering that we don't have right now, so it needs an extreme level of engineering. And of course, we're operating in the middle of West Antarctica, as we were trying to do, needs a lot of logistic support. So it's challenging from several perspectives. Of the 379 subglacial lakes that we know about, and they're scattered all over the Antarctic continent. You can see here, sort of colour-coded by which survey found which lakes. 379. Lake Ellsworth is that one there in the middle of West Antarctica, and you can see it's sort of perched within the brown shade, and the brown shade is relative high topography versus low topography, and that's shown as a depiction here. My colleagues did a ground-based geophysical survey using seismics and radio echo sounding to map out in high resolution the topography around here. And if you didn't know better, if I didn't tell you that was in the middle of West Antarctica, you would be seriously forgiven for thinking that was North Wales. This is it's a U-shaped valley, it's an over-deepened trough, there's a threshold sill just here, there are hanging valleys and spurs and things. It's classic textbook glacial geomorphology that we're looking at here. And the lake sits within the topographic hollow carved out by the action of very small, highly dynamic glaciers at a time when the West Antarctic ice sheet was much smaller than it is now. So our science plan was to undertake the measurement and sampling of Lake Ellsworth using a hot water drill. We're going to use a hot water drill, which I'll explain about in a little while, to get down through 3 kilometres of ice into the lake. We're then going to deploy a probe to get samples of the water, and then a corer to get some sedimentary material, and all of that in completely clean conditions. This is a little animation of our experiment. It's going to be shown you here. So what we were trying to do, the procedure we were using was first to create a cavity of water about 300 metres beneath our feet, link that cavity with the main borehole. The main borehole then goes down into the lake and then comes back. And in the hole that we've created, we send the probe to collect the water samples, which comes back, and then the sediment corer to get the samples from the lake floor, which then comes back, and the hole freezes up, and that's the end of our experiment. So that's what we were attempting to do. To get to the point of doing it, we had to undertake that site survey. It took a couple of years to do that. We had to develop the drill system, took 2 or 3 years, ship it to Antarctica with it over 2 years as well. We had to design and manufacture the probe and the sediment corer, undertake a comprehensive environmental evaluation of the whole project, define sterility and cleanliness protocols, and develop the field site. So it was a lot of work just to get to the point of starting with the experiment. Getting things to Antarctica is quite an interesting route, of course. So any heavy items go this way via shipping containers, a big ship through the Panama Canal, western side of South America, to Punta Arenas. There's then an aircraft that you can use to fly to Union Glacier. I'll show you a picture of that in a second. But all the lighter items like people and other things can go commercial flight to Santiago and then Punta Arenas, and from there a Dash 7 to Rotterdam Station, and then a Twin Otter to Fossil Bluff to Sky Blue, and then to Lake Ellsworth itself. So it's a kind of interesting journey just to get to this bit of Antarctica from the UK. Union Glacier makes the project that I'm about to describe possible. And the reason for that is because it has a vast expanse of exposed blue ice. So the snow and fern has simply been stripped away from here by the katabatic winds, and there's 5 miles worth of blue ice just exposed. You can groom that blue ice, make it nice and smooth. And this is a Russian IL-76 solution aircraft with lots of tyres, with the tyre pressure let down a bit, so it's nice and squashy. This aircraft is designed to deploy tanks in the tundra, so landing on rough terrain is what it's designed to do, and it's actually brilliant at landing on blue ice. I've been on this aircraft. It has 2 pilots, and landing on blue ice is an interesting experience, to put it mildly. You can't put the brakes on the aircraft because you will skid. So you have to reverse thrust 4 engines from its landing speed to 0. And 2 guys are actually wrestling around with the aircraft trying to do this. So I've actually only done this once. And I had so when we landed, I had no idea whether it was a good or bad landing at all, because I'd only had one experience, that was it. So I thought it was kind of jolly interesting. But I was talking to other people on the same plane. They said, no, that one was a bit slippy. I'm not quite sure what they really mean by that. But maybe if we do it again, I'll know about it. Anyway, but this is a brilliant aircraft, and of course, what it's got is a big payload, and heavy items can be put in that payload. So we can get heavy items from the UK to West Antarctica via this route. But we still need to get it to Lake Ellsworth, and what we do is, from Union Glacier, there is a crevasse-free route all the way to the Ellsworth Mountains. Well, the first time we did this project, the first time we designed it, there was a crevasse-free route, but it was much longer than the one I've got here. Then the people at the British Antarctic Survey said, well, actually, we've got a better route. It's much quicker. We can save quite a lot of fuel if we go a different way, but it's not crevasse-free. I said, okay. So these little circles are where the crevasses are. I said, okay, so the good news is we know where they are, the crevasses. All right, well, that's good. That's good news. I said, how big are they? They said, well, they're about 1 metre wide. Oh, that's quite wide. But it's nowhere near as wide as the wheelbase, the caterpillar tracks. So that's okay. I said, how deep are they? We don't know. We don't know how deep. Well, let's not find out. Let's do it. Anyway, this shows you, this is the tractor train that we had with all the equipment on it, and this is the airborne photograph showing the path of the tractor train on its way onto the plateau in West Antarctica, so crossing various crevasses, so it did it pretty well. And this is the depot that we left in the first year, coming back last year to complete the design of the experiment, which we then started. So the drilling procedure is as follows. We had essentially a hot water drill. We have to melt some water, pump it into a boiler, get the water up to a nice hot temperature, put it through a load of pumps, get it to 2,000 psi, and then that water either goes down what we call an umbilical hose, which has got a pump on it, and that allows us to build a big cavity of water. The procedure that we wanted to do was link that cavity with the main hose and go down. What I'm going to tell you later is the reason that we didn't work, the reason we failed to do the experiment, is we couldn't make the cavity link between the main hose and this big ball of water that we had developed for ourselves. And the focus on our attention to the future is how we deal with this issue that we can't allow to reoccur. But we did an awful lot of engineering on this project in terms of development of the probe. This is what it looks like. It has instruments on the bottom end, it has power supply and communications on the top end, and a whole series of sampling chambers in here. There's 3,000 components into this probe, and these are some of them, and each one of these components had to be cleaned by scrubbing, by bathing in biocide, by being subjected to autoclaving and hydrogen peroxide vapor, so that they are absolutely clean. We're using high-grade titanium for much of this as well, because it's easy to clean and doesn't corrode. When this probe has been developed, we have to assemble it ideally in a clean room. If we were building a satellite, we'd have a full clean room to do this, but we couldn't afford that, so we had a clean tent. But with a series of glove compartments. So we had to assemble this probe using glove compartments like this, and the tent was full of hydrogen peroxide vapor, keeping it nice and clean. We then put a bag over the probe, we put a transit case over the bag, and then that was nicely sealed and ready to go and be deployed into Antarctica. It would only come out of that bag once it's in the ice, in a sterile hole that we've made for it. Thus it would never become in contact with the contaminated air. And so that was our procedure for keeping things nice and clean. Similar thing for sediment core as well. This is it being tested in a lake in Austria. If we can get through the sort of over-compacted sediment of an Austrian glacial lake, then we could pretty much deal with the stuff at the bottom of Lake Ellsworth. That's what our thinking was, and it's worked pretty well. So what I'm going to do now is take you through my diary of events from the 1st of December 2012, when I deployed into West Antarctica. I've got a series of animations and videos and things to show you. And what it will do is it will basically allow you to come with me through my journey that I had in the 25 days from the 1st of December to the 25th of December. And in so doing, you'll appreciate the ups and downs and the project as it unfolded on the ice. So day one, we're there. The engineers have been there for some time, setting up the site, and we are interested and excited and raring to go. This is what the site looks like. This is our sleeping accommodation. This is our mess tent. Generators over here. This is where the science takes place itself. We've got a big mound of snow that's been bulldozed up, and we're going to use that, shovel that into 3 onion tanks just there. That's going to be our initial water reservoir. Before we create that big cavity of water, we needed all that water at the surface to drill down. That's what the mess tent looks like from a distance. All the probes are in these big boxes, all in the sealed bags, ready to go. Loaded line of spares for various equipment things up there. It's fine. The fuel are in these bladders. Generators are over here, so it's quite a complex, big can that's been set up. It's a slightly out of timing of this is slightly wrong, but this is what the onion tanks look like when they're full of water. It takes a lot of shoveling of snow to get the water into those tanks, I can tell you. Well, melt the snow as well, but it's a lot of work. We had a bit of power and muscle on site. This was a snowcat that was used to do some heavy lifting for us, which is pretty good, and the first video. Thank you.
So my name is Martin Siegert. I'm the Principal Investigator of the Lake Ellsworth Consortium, and in a few days' time we will be drilling down through 3 kilometres of ice at this very site into the subglacial lake, Lake Ellsworth, that lies below. Just behind me are the wonderful Ellsworth Mountains, with Mount Vincent, the highest peak in Antarctica, at about 4,000 metres above sea level. So I just wanted to take an opportunity to explain to you the general size and shape of the lake, Lake Ellsworth, that we'll be drilling into very shortly. 3 years ago, colleagues of mine, Andy Smith, John Woodward and Neil Ross, spent several months here mapping out the lake and the landscape, and we've got a very good idea about the size and shape of this feature. It's 10 kilometres long, 5 kilometres in that direction, 5 kilometres in that direction, and it's about 2 or 3 kilometres wide. The lake itself is contained within a topographic valley carved out by the action of small dynamic glaciers, much in the same way that areas of North Wales and the Lake District would have been as well. The ice sheet then subsumed that topography, and where water forms at the base of the ice sheet, it collects in subglacial hollows. And so the lake itself is contained within a former valley, and over a deeper part of that former valley, and it's underneath 3 kilometres of ice. The seismic soundings that we took showed at that time that the water depth itself is about 150 metres deep. So the challenge for us is to drill down through 3 kilometres of ice into a lake 150 metres deep. So in terms of glaciology, to my left is the ice divide. The other side of that, the ice flows very gently away to the South Atlantic. To my right, ice flows all the way down to the Pacific Ocean. Very slow flowing ice at this site. Ice is velocity of ice about 5 metres per year. And so it takes several tens of thousands of years to get to the coast. But it makes it very good from a drilling perspective because the ice doesn't deform very much. So the task for us to do in a few days' time is to drill down through 3 kilometres of ice into subglacial Lake Ellsworth, 150 metres deep.
So I had to do that twice. That was all done in one take. But the first time I did it, I kind of got my left and right sort of mixed up. And I was thinking, Atlantic that way, or is it that way? I thought, oh, someone's bound to know. Right, bound to get pulled. I'll do it again. And some of the words weren't coming out very well. It's because the second time I did it, I was getting really cold, and my jaw was starting to freeze up. So I keep things going. Anyway, not a problem right now. So the 2nd of December, we're drilling the head. So we need a hole, and so we get the shovel out, and we dig a metre down, and this is it. And this is the start of the hole, and then we get an auger out to drill a few more metres, and that is where we're going to put the hot water hose and drill further down. So that's just the start of the project. We then put a cap on top of that, and that's where we're going to attach wellhead devices to keep the probes and things nice and clean before they get deployed into the hole, but I'll show you about that in a second. Okay, so 3rd of December, the drill system's been worked up. So minor problems reported, the load cells weren't working. The load cells tell you how much load there is, how much strain there is on the hoses as they're being reeled off the big containers. And we thought this, well, the engineers thought this was a sort of minor problem, they could have a workaround. It turns out, actually, looking back on everything now, that this was a major problem, and we didn't have a solution to it. We thought that we could find a workaround for it, but the result is that we didn't have a workaround for it, and this was actually much more serious than we thought about at the time. Otherwise, the instruments are working okay. So some people trying to get the load cells to work. You see this, they think it's a minor problem because they're all smiling at the moment, realising it. So the idea is we're going to deploy a probe and a sediment core from their exoskeleton transit cases in their bags, nicely sealed. We don't want to disrupt that seal or break the bags. We want to deploy it into the hole without contamination with the air. Clearly, that's something which is going to take some practice, and so we spend hours and hours and a few days practicing deploying these probes and then bringing them back into their sealed bags to see how well we could do it. And so this is Ed Ward trying out the glove compartment, a colleague of his, Rob, doing the same sort of thing. We've got hydrogen peroxide vapor going in one of these hoses and then out of one of these hoses. So the HPV is all in here, keeping things nice and sterile. And then once we're happy with that, we close the door here, open a door on this side, hydrogen peroxide vapor floods in, and then we keep all this nice and stable. So that's how we can deploy various sections of the probe and keep things nice and clean. That's deploying the wellhead to, again, deploy, it's another glove compartment. You see some gloves just down here. It's going to do that same type of job as I explained. And we have to lift the probes. These are quite heavy things, of course. The probes are about 20 centimetres wide, but they're about 5 metres long. And so, and they weigh quite a bit. So we need some heavy lifter to do that. This is a UV probe, but this one is the gravity core, which is the heaviest of the lot. And our Snowcat did a good job in doing that. So I'm going to show you an animation in a short while of deploying one of these probes right now. Oops. And it's a sped up time sequence because it takes about an hour and a half to do this, and over that time, it's much better doing it this way. And so this is what we're doing. There's quite a lot standing around right in this, so apologise for that. And people who are mostly standing around is me. So there, I'll point out where I am in a second. So what we've done is we've taken the UV probe. This is a UV probe out of its container. The blue stuff is just insulation, and we've attached it to the wellhead. It's now been exposed to hydrogen peroxide vapor. That's enough of that. They're going to then take off all the cladding, and then kind of concertina that bag down. It's going to go downwards into the ice sheet. There it goes. And they're going to put some more HPV on the top. That container is going to, because it's on a rail, it's going to be pushed over the top of the wellhead, just there. A second, there it goes. That's nice. And so now it's in a fixed position. We can deploy, if we had a deep hole, that probe downwards into the ice sheet in a nice and sterile and clean way. So that's all good. Now we're just testing whether it's working and everything, and doing a pretty good job on that. And here comes a bit of standing around. Second. That's me, I'm the one in the dark uniform there. Great. It could have been a lot worse, right? You know. Oh, there we go. So the experiment's over, and that's been successful, and so we're going to deploy the probe back into its bag, everything in reverse order. That's going to come out, it's going to be lifted up on the top of the ice. Again, hydrogen peroxide vapor using glove compartments again, so it takes a bit of time. Every time you use the HPV, it's 20 minutes to expose it, to make sure everything's nice and killed. And then that comes out and put into its box, and that's the job done. So we just tried that so many times, and it worked really well. So 5th of December, bad news. We switched the boiler on, and it failed upon switch on. We didn't know any idea why that happened, but what it was, the failure was a circuit board in the control unit of the burner. We didn't know why it had failed, but we contacted the boiler manufacturer immediately and asked them for a spare. Now, if you've got heavy items of equipment like fuel or another boiler or something like that, there's absolutely no way things are going to get delivered quickly enough for it to be useful. But small items, like people or bits of circuit board and things like that, they can be delivered because the logistics chain that I showed you, it is possible to get things onto the ice within some days. So we reckon it's going to be about 10 days. So we ordered a spare component from the boiler manufacturer, reckoning it's going to take about 10 days to get to us. But we had a spare already. So the spare one, when got put onto the boiler, we just needed another spare in case. This is the boiler, what it looks like. The burner unit is just here. It's like an afterburner of jet engine. The control unit, it's not very good photograph. The control unit is just this black box to here. And there was a circuit board within the control unit that failed. So 6th of December, more boiler issues. Various valves are cracked, pressurization pumps not working. Pressurization pumps needed because the water in the boiler needs to be at about 1.5 atmospheres pressure in order for the boiler to be really efficient, and they weren't working very well. So we had to do some maintenance on that. And that's kind of situation normal when you're in the middle of Antarctica, is that little things, little niggles go wrong, and you have to have the engineering expertise to put them right as quickly as possibly can. So there are just workarounds and solutions that are needed all the time. 7th of December, dual system's working pretty well. The load cells still aren't working. They never will work, as it turns out, and that's a real problem for us, but they're still not working at this time. We're still trying to fix them, I should say, at this moment. The probe deployment testing is going okay, that's good, and loads of coverage is starting to appear. So we've got ITN, Sky, and the BBC, and we're just amazed by how much coverage there was of our project, and we're delighted by that. We've got a website that's doing really well, and everyone's feeling pretty positive about the whole thing. So 10th to the 11th of December, we decided to switch that boiler on again. Remember, it failed the first time we tried to switch it on. Filled it up, lots of snow shoveling to get the water into those onion tanks, more minor problems, but workarounds as usual. And then we turned it on at 8 o'clock on the 11th of December, and it was activated by 9. So that's really good news. That's Andy, he's one of our engineers, pretty happy. So this is good and bad news. The good news is there's smoke coming out the boiler. The bad news is there's smoke coming out the boiler. So it's good news because it's working, but it shouldn't be that sooty. And the reason is we've got a problem between the air mixture and the fuel mixture, so we need to do some work on getting that ratio corrected. It did take a little while to do that, I should say. It was non-trivial, but eventually we did it all right. And then we're just trying to create as much water on the surface as we possibly can, because we want to drill down through the ice. The problem is, you need a lot of water on the surface because the upper 60 meters of the ice sheet in Antarctica, or in Greenland for that matter, is permeable. So if you're creating a hole, a hot water drilled hole in the top 60 meters, any water you put down, you will just lose straight away. So it's like you need water at the surface. But once you get down through 70 meters or so, then that's the hard as nails glacier ice, and that's impermeable. And so what it means is, once you've got a pump in a hole in that ice, you can use that pump to recirculate the water that you just melted. And so you don't lose anything like as much water that way. But getting through the top 60 meters is really difficult, and you need a lot of water to achieve it. So speed is of the essence. You want to get down as quickly as you possibly can, using as less fuel and as less water as you possibly can. So it's filling those onion tanks that we're trying to do, and it's shoveling snow, and this is what it's like. It's pretty hard work. There's quite a few of us, so we managed to do it okay, and there we have it. So 13th of December, that boiler's still smoking too much, fuel mix isn't right, probably something to do with the altitude, but we're not really sure about that still, so we're having a lot of discussions about it. But the umbilical hose has been connected to the second wellhead. The cat pumps, which are designed to get the water up to 2,000 psi, are being primed, and we're nearly ready to go. That's what the umbilical looks like. So we've got a number of different leads in here. One of these is water which is going down. Another is water which is coming back up again, because it's going to be connected to a big pump. And that, once we get through the glacier ice, that pump is going to be used to recirculate the water so we don't lose it all at the surface. That's what it looks like, being deployed into the ice. That's Andy trying to connect the pump to some of those leads. And this is a very good photo, but the cat pumps are all down here, getting that water up to high pressure. This is Rob looking at the filters. All the water that goes into the ice sheet is filtered to 0.1 micron to make it nice and clean. and then you can just see here that we've got two of these. This is a UV radiation light, so all the water that's being passed through the into the hole is radiated with powerful UV light to kill anything that's in it. So we're killing all the microbes and viruses and things, and then we're filtering them out anyway. So it's nice clean water, much cleaner than the glacier ice that it's boring the hole into. So this is what we did, 13th of December. We drilled for 60 meters, but we lost all the water. And then we had a look at the hole that we'd created, and this came out the top. This is the dual nozzle extension. So this little thing here, made of brass, was designed to get down through the ice really quickly. What you can see, it's got a couple of bends, one there and one there. And the reason for that is because the dual nozzle extension is bouncing on the bottom of the borehole. And the reason it's doing that is we cannot control the rate of descent well enough because we don't have those load cells working in the reeler. So the engineers took away the dual nozzle extension, and what that means is you're going to have to drill much slower. But the assured thing is you'll be drilling a vertical hole. That's what we thought. 14th of December, more snow shoveling, more boiler issues, either resolved or being worked around. The pressurization sensors are broken. We're having some problems with the pumps. So we've got to get that water to 1.5 atmospheres pressure in the boiler itself, as I explained. And the pumps needed to do that, had a bit of ice in them, and they weren't working. So we spent the whole night, 3 or 4 of us, stripping them apart, putting them back together again, and doing some. This is me taking a photograph. It's a bit shaky. It's about 3 in the morning or something, so it's a bit shaky. Getting it all sorted out. So the 15th of December, we had some bad news. The boiler was turned on again. We're going to waiting to redeploy that umbilical to go down through the last 10 or so meters into the hard glacier ice, and then the boiler failed again. And in exactly the same way, it was the control board that failed, and this is what the failure looked like. It had a failure just here and a failure just here. This is this bit here is called a varistor, a variable resistor. And what it's supposed to do is when there's a power spike in the electrical system that we were using, it's supposed to divert the excess power into the fuse box rather than affect the rest of the circuit board. And what it did, in fact, was just blew itself up, and it took us some other things out with it as well. So that's not good. And this failure was more catastrophic actually than the first one. So we were a bit concerned, really concerned about that. So why did that fail? Why did the circuit board fail? We had 3 options. Firstly, it had wintered over. Maybe it just didn't like those conditions. Likely didn't like those conditions. The second idea was the power surge, and we thought we had a really good electrical system with state-of-the-art generators, but we couldn't rule out the idea that there was a power surge going around the field site that we weren't aware of, and that was an issue. Third option it was just simply a faulty component that we didn't know about. But I have to say, at this point, 15th of December, it looked like the program was off. However, this is early on in the season, and we hadn't used a lot of fuel, and we had nothing to lose by waiting for that third control board that we had ordered from the UK to arrive. And so we started ticking things over, keeping all that water that we'd put into the onion tanks nice and warm, keeping the boiler ticking over, just keeping things nicely primed, waiting for that extra circuit board to arrive. And we released a media piece on this, and I did another piece to camera.
My name is Martin Siegert. I'm the principal investigator of the Lake Ellsworth Consortium. As you may have seen on the website, we're experiencing some technical difficulties right now that is preventing us from continuing at this moment our exploration of the subglacial lake that lies 3 kilometres beneath our feet. The technical difficulties is something which are not unfamiliar in Antarctica. It's a very hostile environment. It's very difficult to do things smoothly. And we are working with our suppliers in the UK to understand what has gone wrong and to resupply some parts and instruments to re-equip ourselves so that we may continue. One of the good news is that we've found the fault relatively early on in our deployment system, and so we have quite a lot of fuel that is left remaining. If we didn't have that, of course, we wouldn't be able to continue any further, but because we have so much fuel available to us, if we can find a solution while working with our suppliers, we may be able to restart the activity toward the end of the week, maybe on the 21st or 22nd of December. So keep looking at the website and we'll keep people updated with our progress. We're working very hard to make sure things are right here. It's not the end of the field season by any means, and with our suppliers in the UK and the expertise that we have on site, we're hopeful to restart drilling in a few days' time.
Okay. So 17th of December, lengthy phone calls with the boiler manufacturer. Turns out that the varistor that had failed was in fact a faulty component. So that was that. We still don't know, having said that, why that circuit failed. It might well have been that the faulty component was to blame, but it is still true to say it wintered over, and it might not like that, and it is still true to say we might have had a generator power spike going around. So although the faulty component was the likely explanation, that might not necessarily be the only explanation for why that boiler unit had failed. So then we just start ticking things over, and for 3 days that's all we're doing, and on the 4:45, on the 20th of December, an Aleutian flight goes into Union Glacier, and a Twin Otter flight comes over to see us with our new circuit board, and that's really good. So we're really pleased that we have that. Turns out that the circuit board that we've got is an entirely different one to the first one. So not only is the component being changed, actually the circuitry has been changed around as well, which probably means that that board had some issues with it, I suspect. So efforts to restart the boiler are proving difficult. The problem was that when that second unit failed, the knock-on failures meant that the LCD screen that it was talking to, that also blew up. And of course, that allowed us to talk to the boiler. But we had a spare LCD screen from the first boiler unit that failed, and so we just crossed our fingers that, because we didn't know that LCD screen was good or not, we just hoped it was okay, and we pushed it into the second replacement, and it worked. So that's good. But then we had to try and program it, and this is Andy Tate and Andy Webb, minus 25 degrees with their gloves off, trying to program a new circuit board via an Iridium satellite link to the UK to try and do that. It was actually quicker to do it this way than sort of try and read the manual and do it that way. So we're really pleased and grateful to the manufacturers for spending the time with us. Turns out they had more work to do with us, as I'll explain in a second. 22nd of December, so we start to drill again. So that's good. The boiler's not working particularly well. It's not at full power yet, but we don't really want it to be at full power at this moment. But we are concerned that it's not getting up to the required temperature. We bent the nozzle again as we restarted drilling. So we just simply removed it and tried again. And at 10 o'clock on the 22nd of December, that umbilical hose, which is 300 meters beneath our feet, stops, and that's where the cavity starts to form. So that's really good news, and that's a pretty good day. That's the umbilical going in. That's Andy Tate his finger on the 300 meter mark, on 300 meters. There you go. It's just there. So that's all that hose underneath our feet. And another piece of camera. Thank you. I'll tell you about that red coat in a minute.
My name is Martin Siegert. I'm the principal investigator of the Lake Ellsworth Consortium. A few days ago on this website, I explained that we had a problem with our boiler, which was preventing us from drilling down to subglacial Lake Ellsworth. I'm pleased to say that in the last few days, due to a delivery, special part delivery, and also due to the expertise of people on site here, and also with the help of our suppliers in the United Kingdom, we've been able to reactivate the boiler to our satisfaction, and indeed we've now started the drilling process to take us down from the ice sheet surface to subglacial Lake Ellsworth beneath us. And just to my left is the evidence of that. This is a umbilical cord which is taking water at this moment at 60 degrees centigrade down to 300 meters beneath my feet, where a cavity of water is being created. That will shortly be turned off, and to my right is the main hole where we'll begin putting a hose in the next few hours, firstly to link up to that cavity, and then to go the remaining 3,000 meters to the surface of subglacial Lake Ellsworth itself. But you can check our progress on our website, on Facebook and Twitter, and we'll be updating those regularly. So we're really pleased that we're in this wonderful place, reactivating the program. Hopefully we're going to have a successful outcome.
Well, as it turned, we won't. So that big coat was quite interesting. That is a Canada Goose jacket, and it is a serious piece of clothing. It's about 10 kilos, really heavy. And I just thought, I'm just never going to wear it because it's just too bulky. And then one day it got really cold, seriously cold and windy. And it was simply no question. It was just that's going on. It's not even a debate about it. And it's lovely. That coat is horrible outside, and it's just a lovely piece of clothing. It's just great. You can also chart the development of my beard through these videos. You know, it starts off all being sloppy, but it's getting a bit long at this stage anyway. 23rd of December, that main hose is connected to the wellhead, the main hose this is, and we are starting drilling going down. And then at 7:45, everything stops. It's really weird. We've got the boiler working, we've got the pumps working, we've got the winches working. It's a really noisy environment. And then instantly, everything stops, completely quiet. And the reason for that is that one of the generators is short-circuited and has tripped all the others, and all the power's gone down. And that's really bad news for us because we've got stuff in the ice sheet, we've got holes that we're creating full of water, and they're going to get cool and start freezing, and we've got to get things working really, really quickly. So it took us a few hours actually to sort that out, and by 10 o'clock that evening, things are back and running again. Everything happens on the 24th of December. This is where the project starts really and finishes. So the drilling continues, but it's slow progress. At 4 o'clock in the morning, we are about 7 meters above the level of the cavity. So our main hose is where we think the cavity just should be. And so we start to leave the hose there and to build it up. And actually, by 2 hours later, we think we've found a connection between the cavity and the hose. And the reason for that is the water that we're putting down, the main hose, is being balanced by the water coming back up again. So that's good. It turns out that was a misread, and that wasn't the case. What was happening, rather than the water being connected by the cavity, what was happening was the water was coming up the top of the main borehole, was leaking out in the permeable layer in the ice sheet, and then coming down the umbilical hose. And that was a problem for us. The other problem was the boiler couldn't get to the required temperature of 90 degrees. It kept stalling at 70. We couldn't get it higher than 90. And that means that simply we couldn't go down to the lake with it that way. So back on the phone, on the satellite phone, to the suppliers, Ormondy, to see if the settings can be changed. We had a lot of preset settings on this boiler because we didn't want people mucking around with it because it's a sensitive piece of equipment, but we had to get the boiler temperature, the water temperature where it was needed. So this is afternoon on Christmas Eve, talking to the boiler manufacturer, and they did a really good job. And by the afternoon, the boiler was nice and working really well. No soot coming out the chimney, really hot water, just what we need. We've got 90,000 litres of water on the surface. We're really good to go. And that's what it looks like. Okay, and that's the hose, and that's our container. Okay. But the problem was that misread, that initial misread of thinking we had a cavity, because as we went down the borehole again to try and widen it up, suddenly we found we lost all the water. And that meant we had to replenish the water at the surface, and we simply couldn't replace the water at the surface at the rate that we were losing it. And the reason we were losing it now was because the umbilical hose had become stuck in the ice sheet. So what was happening, the water was wicking down the umbilical hose, but once it got stuck, that water had nowhere to go. And so we couldn't pump back the same water. We were simply just losing the water in the snow and fern beneath us. And so that's a real issue. We simply cannot get enough water as quick as we possibly can. And so the umbilical hose is stuck in the ice, and we know it is because we can see the water at 40 meters beneath the ice surface, so we know that's there. And then we did a calculation, and it was quite a sober calculation. We said, well, okay, well, if we hit the cavity now, we've been doing this for 40 hours. Our initial calculations said we should hit, the cavity needs 12 hours to form, and then we should link it immediately when we deploy the main hose. And we've been doing this for 40 hours, so this cavity should be really big by now, and we hadn't done it. And we got to the conclusion that we are simply not going to link this cavity for one reason or another. Added to that, we haven't got enough fuel anymore. We've been running this thing for far longer than we had planned to originally. We used up all of our contingency in fuel, and even if we did link the cavity, we no longer had enough fuel to allow the hot water drill to go down to the lake through the ice sheet at the level that was required. So that was clearly difficult. So it was 12:30 on Christmas morning, and it was we were pretty tired as well. All that snow shoveling to try and create all the water. So sort of looking back on it now, it was a really difficult decision to have to make to call the program off. But actually, there was no other decision to make. It was an easy call. Actually, it's one of those things, difficult decision, but an easy call. And the reality is, 3 hours later, we were packing up. And that was what it's like. You know, the mission's over, and everyone starts putting things in boxes. So our Christmas day was not the greatest last year. It was packing up boxes. We tried to release that umbilical, but it was jammed in the ice, and we couldn't do it. And in the end, we had to cut it out. And that's it. Just just cut out. There was no way we could retrieve it. That's unfortunate. So Christmas Day is a bad day for us last year, but everyone's pretty well resigned to things. And immediately at that point, we start discussing why have we failed? Why did we not achieve what we wanted to do? And this was just the start of a discussion that I've been having for the whole year. I'm making pretty good progress on it, I should say. Please, camera.
Hello, my name is Martin Siegert. I'm the principal investigator of the Lake Ellsworth Consortium. It's very sad for me to tell you that on the late hours on Christmas Eve, I had to call an end to this season's activities at Lake Ellsworth. The reason for that is because the drilling progress we were making, while the equipment was working well, the progress was slower than we had planned for, and we did a calculation which showed us that we didn't have enough fuel to get to the surface of the lake, and for that reason I had to call an end to the activities. This is very sad for us. We're extremely disappointed by that outcome. But we must remember that the scientific reasons to do this work remain compelling. We had hypothesized that subglacial lakes contain unique and unusual microorganisms and that their sediments contain important climate records. And we remain convinced about those things, and we wish to continue to test those hypotheses. The only way to do that is to undertake direct measurement and sampling of subglacial lakes, which is what we're trying to do this time. We've learned a lot of lessons from this particular field season, how the equipment works and how to operate a deep field site such as this. And with those lessons, we will go back to the United Kingdom, we will regather ourselves, we will talk to our funders, the Natural Environment Research Council, and hopefully we will plan a second return season so that we can eventually do the work that we had intended to do this year, and that is to get into subglacial Lake Ellsworth and take direct measurements and sampling of that environment. So for now, it's a very sad moment for us, but we live to fight another day. Thanks ever so much for following us on Facebook and on Twitter and on our website. But for me, Martin Siegert, goodbye.
Well, not quite yet. Not quite goodbye. This is how Christmas, it was, tried to have Christmas, but it didn't really work. So things that went well. Well, we bought a lot of equipment, and that equipment still remains purchased, so that's good. And we designed and built the probe and the corers. That was great. The sterility protocols worked really well. Our comprehensive environmental evaluation that was accepted and agreed with the Antarctic Treaty was good. Deployment system was excellent. The boiler, although we had problems with it, eventually that was fine. We did not. The project wasn't stopped because the boiler didn't work, although that gave us a load of headaches. The experiment field design was pretty good. Pretty happy with that. With some reservations, which I'll explain in a second. And we also characterised the local microbial communities and the native snow and the drill water, etc. The logistics were superb. So, one of the major tasks for us was to understand whether we could do the work in this location. And actually, all the logistics worked fantastically, so we're pleased about that. And the fact that you know about this project meant that our outreach and communications was also superb. Things went badly. The boiler didn't work very well when we needed it to. It didn't winter very well, and it should have done. It should have. That's a mistake that we made. The control boards were initially faulty, and probably because they were from a 40 component batch, and that's just the way that is. Boiler couldn't get up to temperature when we really needed it, but eventually it did. The drill nozzles, drill nozzle extensions bent when we used them, and the reason for that is because the load cells that we were hoping to determine the strain on the hoses, they weren't working, so we couldn't tell when the bottom of the hose was touching the borehole that it was creating. We thought we had some workarounds for that. It turns out that we didn't, and that was a major problem for us. We didn't have enough fuel. Well, we did have enough fuel if things had gone well, but the contingency had been used up, and therefore we didn't have enough fuel ultimately. Shoveling snow, as you might expect, is exhausting, and we need to find a different way of doing that than the way that we tried through manpower previously. And it's fair to say there were last-minute amendments to the drilling procedure, and that wasn't very helpful for us either. So why did we fail? Well, we didn't think the cavity that we created for ourselves. That's one of the things we really needed to do. One of the reasons we needed to make that cavity is the cavity itself had a pump within it, and the pump was being used to circulate the water around. If you don't circulate the water around, the water gets cold and starts to freeze, and you can't allow that to happen. So it's a necessary thing to do. The other thing the pump is there for is, as we puncture into the lake, we need to take out about 300 meters of water from the borehole, because if we don't do that, that borehole water goes into the lake. And we wanted to balance the water pressures of the borehole and of the lake as best we could to minimise the exchange of water between the two. So the pump that we need for that is in the cavity. Drillers don't like putting two strings down the same hole. And so that's the reason we had designed the experiment the way that it was. So where do we go from here? Clearly this is not where we wanted to be and it's not where we expected to be, but it is where we are. And so for the whole of the last year, I've been in discussions with engineers and with the Funding Council and with an independent review of the programme to understand, firstly, why things went wrong the way that they did, what lessons can we learn from that, and how do we put those lessons to good use, how do we get it right? And it's taken quite a while to do that. I'd say around about halfway through the year, I was in a position to say, I understand why we failed, and it's taken us another 6 months to get to the stage now where I can contemplate thinking about the redesign of the experiment. And at the moment, at a meeting on Monday, in fact, at this moment, we've got about 4 different options available to us in terms of modifications to the experiment. And over the next few months, we're going to do some engineering to work out which of those is the best one forward. So it's like I said, it's not where we wanted to be, but it is the situation where we are. The forecast for this still looks pretty good. I mean, so I've been working on subglacial lakes for 20 years. This essentially is an engineering development project at this moment. The engineering has never been done before, and when you look at engineering projects in other places, there are lessons to learn in a very similar way to what we're doing. The difference between this project, which makes it such a high profile, I guess, is that we were trying to do some science with it at the same time. And I think when we do the second experiment, what we will do is not try and couple the science with the engineering development in the same way. We will simply have a project which designs, builds and tests the drill. And when we get that right, then I think we're in good shape to do subglacial Lake Ellsworth 2. I have to tell you, that might take some years, really looking at 5+ years before we get a chance to go back. But it's taken me 20 years to get to this point, so another 5 or so is what you have to do. Thank you very much.
Well, that was great, if not a bit chilly. Martin, I know, is happy to take some questions.
Down here.
Stick your hand up and the roving mics will find you. Oh, there we are, very close at the back.
I'm just interested to know how you budget for something like this. How much does it cost?
Slightly over £6 million for this.
6 million?
Yeah. So
doesn't seem much somehow.
Yeah, so I'd say about 2 million of that was for development of the probes and the corers. We still have. There's a lot of engineering that goes into that. Another $1 million for all the equipment, but a sizable amount, over $1.5 million for the logistics and things put all together. And then in addition to that, you've got salaries of the people that are working on it, of course. And there's quite a lot of person years involved in that. So that's around about the right figure.
Well, let's work our way around this way.
Well, a very interesting talk. You mentioned that the top 60 or 70 metres of ice was quite permeable. Had you thought of trying to use some sort of like stainless steel casing or something to try and isolate that a more permeability zone from the harder ice beneath?
Yeah, thank you. So we have thought of that. The problem with it is that's very bulky stuff that we would have to do, and it would add another layer of complexity into the operation. The experience that we've had with hot water drilling, no one's ever drilled down as deep as we're trying to do, but lots of people have been through the top 60 metres of the ice sheet using hot water drilling and have been successful. And in fact, we were successful as well in getting down. It was just some other parts of the drilling procedure that didn't work for us. So we don't think that is a critical problem that we have. It is a problem that we can deal with. You just need to have sufficient water at the surface. But once you get down through the hard glacier ice, then that's it. So it's just getting to the top 60. It should be quite quick to do because it's not hard ice. It's snow and firn that you're going through. The density is less, so you can get down pretty quickly. One of the things we're thinking about is using that umbilical hose, which has a pump on it, to create both holes initially, because that should be a much more efficient way of getting down through the firn ice, because you can deploy the pump quite quickly So that's in our procedure. We're thinking about, again, that's probably what we would do, but we're not thinking about casing it. If we were going to case it, it would probably be a plastic that we would use. But actually, we have thought about that over the course of the year, and we've still written that off as an idea there. But thanks, thank you.
Keep on moving. What about the gentleman over here? Here we are.
Following on from that question, really, are there any environmental implications of leaving that hose in the ice?
Yeah, sure. Well, we didn't want to do that, and that's a major problem for us. It's fair to say that we spout out all the potential risks with the project from a very early stage, and so then we're very open about that. And the fact that I'm telling you about it is evidence of that. It's also fair to say this is not the first bit of equipment that's been left in the ice in Antarctica. These sort of things happen. It is clean, and so that's one thing that we could say. So that's good. And it's not going to get into the lake. This is only the top 300 meters, and that will just be transported down. I guess the practicality of it is just like doing shipborne work. People who work for the National Oceanography Centre say you don't put anything over a ship that you're not prepared to lose. And it's the same way with an ice sheet. If you're not prepared to lose it, you shouldn't deploy it. So we don't want to, but there's really nothing you can do. Once it gets frozen in, that's it. And it's not a regular occurrence, but this has happened before in other bits of Antarctica. Bits of hose have been stuck into the ice.
Oh, right in the middle. And then we'll go right over that side.
You say it's going to take about 5 years to get back again.
Yeah.
Do you know if any other country is undertaking similar research before you? More generally, is there a sort of protocol as to how research could be carried out? Is there some, do you have to get permission from some organisation before doing so?
So that's a good question. So there are 3 projects. Our project, there's a Russian project at Lake Vostok, and there's a US project at Lake Williams. I'll just describe very briefly what those are, and then I'll answer the second question if I remember it. Right. First one is a Russian project at Lake Vostok. And so Vostok Station sits over the southern extreme of Lake Vostok, and we know about Vostok Station because there's an ice core there which has been used to extract. The ice core tells us about the paleoclimate for the last 400,000 years or so. It's just a brilliant record. Turns out the bottom of the ice core is a few hundred meters from the top of the lake, and so Russians have been using this idea as an opportunity of getting into the lake. The problem with ice coring, unlike hot water drilling, is that it takes a long time to remove the ice, and you can't leave it full of air because the ice would simply close up due to the pressure, stresses and things. So what you have to do is put a fluid in because of the back pressure, and you can't put water in because that would freeze, so you have to use an antifreeze. And what the Russians use is kerosene in Lake Vostok, which kind of means that renders the use of an ice coring hole as not being suitable to try and undertake an ultra-clean experiment into a subglacial lake. I suspect if the ice core was not in its position, the Russians wouldn't be advocating using ice coring to get into the lake, and I suspect if they wanted to do it again somewhere else than Lake Vostok, they wouldn't be using that technique either. Hot water drilling, even though we've had our problems, I'm convinced is the right way forward for clean, rapid, direct access to the subglacial environment. The US program uses a very similar technique to the British experiment, using a hot water drill, etc. But the project that they're working on is on a subglacial lake, which is right at the ice sheet margin, it's right close to where the ice becomes floating and then part of the Ross ice shelf. And from my understanding as a glaciologist, it's just not a particularly compelling target to look at. It's a lake that won't be old. It's a lake that will be having water flushed into it and flushed out of it regularly. It's unlikely the sediments are going to be undisturbed, and so there'll be very little you can tell from a climate change perspective as well. The ice is about 800 meters, which is probably why they had a bit more success than we did. But ultimately, it's not a very good target for that. Now, the next question was, is there a protocol that's been set up for this? To do this type of work, it was long thought that what you needed to do was a comprehensive environmental evaluation of everything. And we are the only project that's done it. So the Russians started doing one, but it got heavily criticized because of the use of kerosene borehole to get into the lake. And so it's never really been fully revised. Bits of it have been revised incrementally, but the whole thing never has been resubmitted. And the Americans decided, because they were so close to the edge of the ice sheet, that they didn't need to do one anyway. So there is a protocol for it, and it's the experiment that we have designed. We will modify that experiment in the light of the lessons that we learned from this, and we'll make a revision of that probably in the next year or so. Thank you.
And this will be the last one. Far away. Where have we got? There we are.
Hello. Would you anticipate there to be a head of water upon encountering the lake?
Certainly. So the answer is no, and the reason for that is because if you get a head of water like a spring, like the water that comes out, it's because there's a water table that's been elevated somewhere distant. The water pressure is pushing it down. It's coming up. This can't happen in the middle of West Antarctica, and the reason for that is because all the water is beneath your feet. So it's highly unlikely the water's going to gush up. If it's, it will be under pressure, but that pressure will be the weight of ice that's over it, and that ice will be floating in the lake. So if anything, once you puncture into the lake, it's not the lake water that will come up the borehole, it's the reverse. It will be the borehole water that goes into the lake. 3 kilometres of water weighs more than 3 kilometres of ice. And so we have to take out 300 metres of the water to try and get that balance right, as well. We need that pump in the place. But it is fair to say that it's not the water pressure that we were mostly concerned about, but there was an outside chance, remains an outside chance, that there may be gases in the water, especially if it's very old. And the reason for that is we know that gas is being put into the lake because the ice contains gas from the air, from the snow that it was first formed in. And at Lake Vostok, at least, we know that there is accretion ice. That's ice, that's water that's frozen to the underside of the ice sheet and then gets taken away. At Lake Vostok, that accretion ice contains virtually no gas at all. And so we know at Lake Vostok there is an input of gas and it's not balanced by the output of water. So the gas would accumulate in the lake. And there's been some scary calculations, I mean, on the stream edge of being likely also, that there's enough gas in the lake, that similar level of gas as in like a can of Coca-Cola. And there's an irresponsible comment that, well, if you go into the lake, it would be like a can of Coke popping off, but it really won't be like that. But nonetheless, you get the idea of how much gas there could be. We had no idea, of course, whether those processes going on at Lake Vostok are going on at Lake Ellsworth. We haven't seen the same type of data that hints at those processes at Lake Vostok. We haven't seen that data in Lake Ellsworth. But absence of evidence is not evidence of absence, right? So we couldn't tell. So we did have a protocol called Operation Vinegar, right? And Operation Vinegar was when we were just about to go into the lake, all the non-essential people would be several hundred meters away from the site, just in case. So I thought this is like, health and safety and all that gone kind of mad. But at the same time, if you ask me, do I want to put my head over the borehole when we go into it, I probably wouldn't do that. So we had thought about it. It's not the pressure of water. It's the outside chance there being some gas. We were very cautious about that.
Well, thank you, Martin.
Thank you.
Thank you.
Thanks very much.
Well, we've had some wine on ice, I think, while we've been talking. Let us go next door.
Thank you.
Thank you very much.
Pleasure. It's a pleasure.
Just checking mics off.
Yeah.
I would caution you to escape quick,
Yeah.
otherwise you will get some ambush.
No, that's fine, because I'm happy to answer one here. I want questions and I want people